Welcome to sixth part of kinetic theory. In this part, you will learn about specific heats and Dulong's and Petit's law. Specific heats of monoatomic, diatomic and polyatomic gases. Let's calculate for monoatomic gas first. In this case, you know the degrees of freedom are 3 and according to law of equipartition energy, the average energy associated with each degree of freedom per molecule is half kBt. So the average energy associated here will be 3 by 2 kBt. And in terms of total energy of 1 mole of monoatomic gas, it will be 3 by 2 kBt into Avogadro number Na. And you know that kb into n is R, the gas constant. So the molar specific heat at constant volume will be du by dt. That means you have to differentiate 3 by 2 RT with respect to T and you will get 3 by 2 R. And by Mayer's relation, Cp is equals to Cv plus R. So just add R in 3 by 2 R and you will get 5 by 2 R. And the specific heat ratio gamma is Cp by Cv. By putting the values of 2, you will get it as 1.67. Specific heats of diatomic gas. You know that the degrees of freedom are 3 translation and 2 rotation means total 5. So the value of U will be equals to 5 by 2 kBt into N. And by following the same procedure as we have done in the monoatomic case, you will get the gamma value as 1.4. And if the diatomic molecule is not rigid, then it will have the vibrational energy also. So you will get the 7 degrees of freedom. So the value of U in that case will be 7 by 2 RT. And similarly, by following the same procedure and find out the value of Cp and Cv, then the gamma value will come out 1.28. For triatomic gas, you know that we have 2 types of degrees of freedom. If it has 6 degrees of freedom, then the value of U will be 6 by 2 kBt into N means 3 RT. And for this, the value of gamma will be 1.33. And if it has 7 degrees of freedom, then the value of gamma will be 1.28. Similarly, if we have to find out the general formula, let us suppose we have a polyatomic gas and the degrees of freedom are F, then the average energy of each molecule will be F by 2 kBt. Then the internal energy will be F by 2 kBt into N means F by 2 RT. And the value of Cv will be du by dt, that means F by 2R. By differentiating it, and by using Mayer's formula, Cp is equals to Cv plus R, you will get Cp equals to F by 2 plus 1 into R. And the value of gamma will be 1 plus 2 by F on solving. In case of solids, Dulong and Petit observed that near the room temperature, the molar specific heat of most of the solids at constant volume is 3R or 6 calorie per mole per Kelvin, or you can say 25 joule per mole per Kelvin, and is known as Dulong and Petit's law. To prove it, in a solid, you know the atoms vibrate about their mean positions. And during vibration, the kinetic energy of an atom changes continuously into potential energy and vice versa. So the average value of kinetic energy and potential energy are equal in solids. And since an atom can vibrate along 3 mutually perpendicular directions, so it has 3 degrees of freedom. And by applying the law of equipartition energy, Ek will be equals to 3 into half kBt, and similarly Ep will be equals to 3 into half kBt, and the total average vibrational energy per atom you will get 3 kBt. So U will be equals to 3 kBT into N means 3 RT. And because for a solid, delta V is negligible, so delta Q will be equals to delta U. And you know that CV is equals to delta U by delta T, so it will be 3R. Here is a variation of specific heat of a solid with temperature. And you can see that the temperature at which the molar specific heat of a solid at constant volume becomes equals to 3R, and that temperature is known as Debye temperature. In case of water, by law of equipartition energy, average vibrational energy per atom will be 3 kBT. And you know that in water, H2O, it has 3 atoms, 2 hydrogen and 1 oxygen. So average vibrational energy per water molecule will be 3 into 3 kBT means 9 kBT. And multiplying by N, you will get the U as 9 RT. And neglecting delta V like solid, you will get delta U as 9 RT, and CB equals to delta U by delta T means 9R. And this predictive value is found to be good agreement with the observed value. So the specific heat of water is nearly 75 joule per mole per Kelvin, or you can say 9R. This graph shows the variation of specific heat of water with temperature. We have already discussed this graph in the earlier unit and defined 1 calorie as the amount of heat required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius.